Okay, welcome to this tutorial about designing a heat exchanger. In this tutorial I will show you how to design a heat exchanger in Aspen, but I won't tell you everything because for instance the calculations for the heat transfer area, they are part of the assignment. So I will only tell you what is necessary to design a heat exchanger in Aspen and not designing the heat exchanger with calculations. Okay, so but we have got this hot stream here, hot in, and it is a stream of 60 degrees, 10,000 kilograms an hour, pure water, and we want to cool it down 20 degrees. And we want to do this by cooling it with a stream of cold water of 10 degrees, and the specification is that the cold water can only warm up by 5 degrees Celsius. So, and we want to know um, we want to design a heat exchanger for this, and the way we do this is first to see how much energy has to be transferred, and from that we can calculate our heat transfer area. So first what you do is you take a simple heat exchanger or a heater, and a heater can also be a cooler, but that's just the name Aspen gave it. Hot out, although it's cooler, it's the hot stream out, and we want to change the temperature to 20 degrees, and we don't want to introduce any pressure drop, so we just leave this as it is. Um, we don't want to have any vapor, we want only pure liquid. So if you have conditions where you can get vapor, make sure you change the inlet conditions, maybe change the pressure or the temperature, uh, so that you don't get any vapor in your heat exchanger. Okay, yeah, we got a warning, but that's not important because this is because we are only using one component, water, and not two. But let's see. Okay, so we put in 60 degrees, uh, like a stream of 60 degrees in the heater, and the heater will cool it down, or the cooler will cool it down until 20 degrees. And you can now look at the results, and you can see, yeah, it's not a really handy unit, but let's put it on kilowatt. So we need to cool the hot stream uh, by there has to be a heat transfer or heat duty of about 400 kilowatts to cool the stream down to 20 degrees, from 60 to 20 degrees. So now we can calculate how large the stream of the coolant should be. And the way we do this is we take another heat exchanger, and this is going to be our cold stream. So cold in, cold out. Okay, and the cold stream is a stream of cold water with a temperature of 10 degrees. Also pressure, now we can make it the same. And so 6 bar, as long as you don't get any evaporation. Okay, and we'll just start with 10,000 kilograms per hour, and we'll just see what happens when we cool the hot stream. Okay, let's just see if this works. Oh yeah. So we have to fill in some specifications for the heater, and now we already know what kind of duty it should do. So we can select heat duty here, and we can fill in the number we obtained here from the first heater. So in the pressure, we won't want any pressure change, and we do want to have only liquid. And now we can see what happens. Okay. Let's see. Is there some problem with the... Oh, yeah, this is a mistake of mine. Mass fractions, of course. Okay, so now we can look at our results, and you can see our cold stream has warmed up by 41 degrees. So this our stream is too small to get into range of the 5 degrees temperature increase we want. So we can enlarge the stream. So maybe take 40,000 and see what happens then. Okay, so we're getting there. It's only a 10 degrees difference, but we want a 5 degree difference. So maybe 680,000. Let's just see. Okay, so now we have about 5 degrees difference. Another way, if you want to have an exact number for the flow, you of course can make a sensitivity analysis. I can show you how to do this. So what we want to measure is the outlet temperature, and we want to change the inlet the inlet flow. So we will make a new variable. It's a stream variable. This stream number, the stream name called in, and we want to change the mass flow, and from 1 to 80,000 kilograms per hour, 100 points. Then we want to measure the outlet temperature. It's also a stream variable of the cold outlet stream. Okay, and of course we want to tabulate this. Now we can run it. Now we have some errors. Let's see. Okay, we have one error in the beginning. Maybe we shouldn't. Yeah, I think we have a phase change because we have our stream, our sensitivity analysis begins at 1 kilogram per hour, and this means that the stream is heated up so much it will evaporate even at 6 bar. So maybe we should try 1000, and maybe we won't get the error anymore. Okay, so no errors anymore. We can check the results, and we can of course plot this. So we vary the mass flow in, and we plot the temperature of the outlet stream. Okay, and now we can search for the point where the temperature is only 15 degrees. So we have to change the axis a bit, I think. One moment. Oh, I put in here 80,000. Maybe we should broaden the range a bit to 120,000. Okay. Now let's see. So now from 0 to 20 degrees, and from 50,000 to 120,000. Okay, so 15 degrees. I think it's somewhere here. So I think it's about 82.5. If you want to have it more precise, so here you can read it. You can also let Aspen calculate the exact point, and you can do this um, with a design spec. But since the last time this didn't work, okay, you have to be careful with this. We can delete this sensitivity first, or hide it. We just hide it, and we can do a design spec now. I will create a new design spec, BS1. We define um, what we want to spec. So I want to spec our temperature. So that's the outlet temperature of the cold out. And our target value is 15 degrees with a tolerance of 0.01. And we want to vary the flow of the cold stream. So the cold in. And we want to vary it from 90,000 until, no, that's from 50,000 kilograms per hour to 120,000, because we already know that it's in between these borders. So let's try this. Okay, so it probably did it alright. And now we can go to our flow sheet, and it says we need 83,977 kilograms per hour to exactly get a 5 degrees temperature difference. So with these numbers, we can now design our Heatx model. And what is important is that you take exactly the same stream and conditions you have used for these two heater blocks. You have to select, yeah, let's see, you have to put in a cold stream here and a hot stream here, and so you also have to make sure that the actual hot stream is going into the hot side. So if you connect them wrong, Aspen will give an error. So this is our cold stream with the cold out, the hot stream with the hot out. Let's give them names. So this is cold in 1. This is cold out 1. We can do that. Cold out 1. Hot out 1. Hot in. Okay, so now we have to specify our streams. So, and this was 10 degrees C, 6 bar with a mass flow, and we have to copy this from the other one, but I think it was 83. So yeah, exactly the same. Then we have to also fill in our hot stream. This was 60 degrees, 6 bar, and 10,000 kilograms an hour of water. And make sure I also put in mass fractions here. Yeah. Okay. So now we have to specify our Heatx block, and in the beginning, just to get a rough estimate of the heat transfer area, you will set the calculation method on shortcut and the type on design, and we want to specify our heat exchanger on the basis of the exchanger duty, and we already calculated this, so we can get it from here. It's nicer if you have this in kilowatt, but in this case it doesn't really matter. Okay, so we fill it in, and I think we can now run the Hetex block. Let's see what happens. Okay, one additional warning. I don't think it's a problem. Okay, so but now we've made a quite a simple model for the heat exchanger, and we can look at the results obtained from this Heatex model. And what it did, because you've used the shortcut and design method with a phase-specific U value, like these are the phase-specific U values, and these are just values Aspen has used to calculate the heat exchanger area. So these U values don't have to be the real values of the actual heat exchanger. So, but it will give an estimate. And I think in the assignment, in the Word file, there is a list at what kind of U value you should expect. So you can take this, or you can use the constant U value and fill it in, and take the like the initial gas you get from the assignment, and after this you can change it to a more real value. So you can look now at the results of the heat exchanger model, and you can go to exchanger details, and you can see this is the heat duty we filled in, and he calculated an exchanger area of 22 square meters. And we can now also show you what happens if we change the U value, and it's now like 730, but if we would take a value of 1500 for instance, and I hope it's the same unit, yes, so 1500, and now let's see what happens to the result of the heat exchanger. Yeah, like our exchanger area has is now half the size, because our overall heat exchange coefficient has increased 2 times. So we have to we first take an initial gas of the U. We will calculate, or let Aspen calculate, the total required exchanger area, and from this area you obtain here, you can calculate how long, how many tubes you need in your heat exchanger. I already did this, and since this is part of the assignment, I won't go into too much detail, but I just will show you how you can fill in the numbers if you want to use a more realistic heat exchanger. So if you want to have a more realistic heat exchanger, you go to you will fill in simulation here, and you will use the detailed model. You also have to choose which side you want to use for the hot fluid. So do you want to have the hot fluid on the shell side or on the tube side? I will put it on the shell side, but I think it's most convenient to use the biggest stream, so the largest stream, so the most cubic meters per hour on the shell side, because it's quite hard to introduce pressure drop there, and always use counter current. Now you will have to go to U method, because we first fill in a constant U value, or a value that Aspen used, like this, but now we want to let Aspen calculate the overall heat exchange coefficient from the exchanger geometry, so from the way the heat exchanger is put together. So if you change the number of pipes, or you have higher velocity in the tubes, or you change something about the geometry of the heat exchanger, also the U value will change. So that's something you have to keep in mind. And now you can go to the geometry tab here, and you can fill in uh, the values of your from your calculations which you think are right for the design of a working heat exchanger. I already did this, and I hope it will work in this case. So I have some numbers here I will fill in. If you want to start with making a working heat exchanger, just fill in numbers that are um, yeah, like um, bigger or in the range that just works. So if you have um, you can always in the beginning make the shell diameter quite big. This is not realistic, but just make it big, so at least everything will fit inside the shell. And so there are a few things that are not realistic in the beginning, but we can change them later on to make them work. I have some numbers that already work, and I will fill them in, and we will see if we can get a working heat exchanger. But it's always good if you start designing the heat exchanger to begin with tubes, because the tubes are the hardest thing to get right. And if you first do something else and then want to adjust the tubes, everything will change again. So begin with the tubes and get them right. You can use actual sizes for the tubes, but I think it's quite convenient to use the nominal. Um, so you can just select diameters that are used in industry. I will select this one. If you want to, you also have to fill in the pitch, and quite a normal number for the pitch is um, 125% of the outside diameter of the tube. And that's not the case here, but I chose this for now. And this is the thickness of the tube. So the thicker the tube, the higher the pressure you can reach with the tube, but I will just take the smallest one. This is where I've cheated a bit, because I took more baffles than was allowed by the assignment. But that's because my cell side stream is too small to introduce enough pressure drop. Okay, we get an error here. Okay, so it says that our shell diameter is smaller than the bundle of tubes. This is a bit weird because I already did this before, but I will override this first. And the nozzles, nozzles are the inlet of the heat exchanger. We will just make them quite big, so there is no pressure drop over these nozzles. Okay, let's see. It's here. Let's see what works. Still not 0.4. Okay. Let's see, does this work? This is quite weird. Okay, I already see what I've done wrong. 100. These are not in the same units, so it's not even close to 125%. So let's change this to inches. not very convenient to calculate in inches, but since the diameters are only in inches, it's convenient to take the pitch also in inches. Okay, so 80 tubes. Now I hope it's okay. Okay, so now we can look at the results again. So you can see our exchange area is now close to 11, and our outlet temperature is also alright. But this is because I already calculated beforehand. You can also look now at the pressure drop and the velocities. You can see that you have a pressure drop on the shell side of 0.32 bar, so this is in specification with the assignment. The tube side is a little bit high, but yeah, I can make it lower, but then yeah, the temperatures are less yeah, less within specification, so that's just what you have to choose. Also the speeds are quite alright, I guess. One thing that is important, you don't want to have the pressure drop on your nozzles, you want to have the pressure drop over your heat exchanger. So if you have only pressure drop over the nozzles, this is wrong, because you want pressure drop over the heat exchanger, because there the heat exchange takes part, and not in the nozzles, because the nozzles are the inlet connections of the heat exchanger. So if you make them very small, you can get very high pressure drop, but you won't get a really good heat exchanger. So that's something to keep in mind. Yeah, now you can also see the real U, the overall heat exchange coefficients, and so it's yeah, around 1400. I don't know if it's, I think watt per square meter is a more common unit, and I think it's also in the assignment. So it's 1600, and I think it's a little bit higher than the table in the assignment was predicting. So but you have to try to get if you don't reach your temperature values, or your it cools too much, it does the heat exchange too good, you have to decrease your exchange area. And if it doesn't cool or heat up the way you want it, it does too it doesn't have enough heat duty, then you should increase square meters and do the calculations to get your number of tubes and the length and the heat exchanger area. Okay, but I hope you will I taught you enough to design a good heat exchanger, and otherwise you can always ask in the working sessions.